Welcome to Linear Engineering. On this channel, we discuss mechanical engineering in general and simulation in particular. We also discuss the ramifications of mechanical engineering, especially technical mechanics. And it is from this perspective that we will address today's topic, which is kinematics, displacement, deformation, strains in continuum mechanics. This is the content of the presentation. We will talk about body motion. We will show what is the difference between Lagrangian and Eulerian description. We will also talk about a displacement. We'll define a displacement, deformation, a strain. We will also show how to rewrite strain, for example, in principal strain axis. We will talk about spherical and deviatoric strain, material time derivative, what is a rate of strain. We will talk a little bit about objectivity in continuum mechanics, and finally we'll do a summary. So, a body is made up of material points. We can think of a material point as an infinitesimal small part of a whole, which can carry material properties. Infinitesimal small means such as the body consisting of these points has a continuum character rather than a discrete one. So the motion of a body is the transition from a configuration at a given time to another at a later time, like the figure shows. So a body moves from a reference configuration at a time t0 to another configuration at a later time t. A configuration is a geometrical and spatial state of the body, and the configuration is called reference because it is the start of a motion, and we evaluate the end of a motion with respect to it. We will use uppercase letters for the reference configuration and lowercase for the spatial configuration. The body material point with a position material x, upper x, moves from the reference configuration at the time t0 to another configuration at a later time t, which now is a new position lower x or spatial x. So material x of a reference configuration is in material coordinates, and lower x, spatial x, the new position after the motion is in spatial coordinate. The motion is the bijective mapping spatial x equal phi of material xt. The motion is the bijective mapping spatial x equal phi of material xt. A bijection is needed here because every material point must be mapped to a new distinct position, and the reverse motion to the initial reference configuration must be possible. Further, we request the overall derivability of the mapping function phi, because like we will see later, this is needed by some important quantities variables. Continuum quantities in Lagrangian description are bound with material points of a body. Their changes are first expressed in material coordinates. The Eulerian description quantity changes are registered from a fixed spatial position. Quantities are first expressed in spatial coordinates. Quantities can be either in Lagrangian or in Eulerian description. And quantities are material properties, velocity, temperature, stress, strain, etc., bound with material points of a body. Bound with material point of a body means they evolve with these points through the course of a motion, in contrary to the fixed position case, where several different material points pass by with time. This lays the ground for the choice of either of them whenever we are slowly interested in some spatial position changes or in evolution of the quantities themselves throughout the motion. We can still change the description, or we can switch the description and vice versa. So to show how displacement and later deformation works, we define two neighbor body material points, A and B, with the coordinate on the slides. The coordinates of both are of course in material reference frame. Between A and B is the infinitesimal vector d material dx. This vector is displaced in the spatial configuration in lower dx. With a displacement gradient of u equal partial derivative of u with respect to material x, which records the ratio of geometrical change in material dx, the displacement reads spatial dx equal material dx plus partial derivative gradient of u times material dx. So we can conclude that the displacement and this gradient encompass both rigid body motion and actual pure deformation. The aim of continuum mechanics is to develop constitutive equations about cause and effects of a body motion, about strain and stress, etc. And for that, we need to tell rigid body motion from deformations. Fortunately, the displacement gradient matrix is square. The displacement gradient tensor is a square tensor. It is first the addition of its symmetric and its skew symmetric part, which are respectively responsible for deformation and rigid body motion. So the symmetric part is gradient of u symmetric equal 1/2 open bracket gradient of u plus transpose of gradient of u close bracket, and the skew part is gradient of u skew equal 1/2 open bracket gradient of u minus transpose of gradient of u close bracket. And gradient of u is of course the addition of both parts. So with a mapping function, we can get to the deformation by setting spatial xa equal phi of material xat, spatial xb equal phi of material xa plus dx t, spatial dx equal xb minus xa. It is also the partial derivative of a mapping function with respect to material coordinate times material dx. In this expression, the deformation gradient tensor is then this partial derivative of phi of material xt with respect to material coordinate. It's also equal partial derivative of spatial x with respect to material x, and finally equal to identity plus gradient of u. As we can test, this deformation gradient tensor don't vanish when the displacement gradient is 0. That means when, for example, we have only a rigid body motion, because the identity term will remain. So now that we have the deformation gradient tensor, we can describe how geometrical elements like lines, areas, and volumes are deformed. A line material dx in material configuration is deformed through norm of spatial dx equal square root of transpose of f times f times norm of material dx. So for an area, we first know that the norm of a cross product of two vectors spreading an area is the content of this area. The normal vector, which is of course the cross product itself. We also have a variable named Jacobian, the determinant of the deformation gradient tensor. We'll see right why the Jacobian is very important in the context of continuum mechanics. So with these prerequisites in hand, the special dA is normal vector times dA is time j times transpose of inverse of f times material n dA. Using these equations that we learned until now, starting specifically with a cuboid, we can write the general deformation of a volume as dV equal j times dV, material dV. So dx1, dx2, dx3 is obviously, this term is obviously a volume, and we find again the Jacobian. So why is the Jacobian very important? Special dV equal j times material dV means j must be greater than 0 in order to preserve a physical phenomenon of a volumetric deformation. So 0 means volume force material vanishes and negative j values is physically impossible. So this fact must be remembered whenever the Jacobian is met. So in the next stage, where we will deal with strains, we want to have a quantity which measures exclusively pure stretches. The deformation gradient tensor F don't. Besides stretches, it records also rotation of a body through composition of and when we look at the derivative in this tensor, it encompasses coordinates of both material and spatial references, which with lower and upper x. However, since it is a second order tensor and non-singular because of a Jacobian being positive, we can decompose it in an orthogonal and symmetric positive definite tensor. The orthogonal tensor is then the rotation, and the symmetric positive definite one, the wanted pure stretch. It reads F equal R times U equal V times R, with U and the material and V the spatial stretch tensor. They are also called respectively right and left stretch tensors. In RU, the material point is stretched and then rotated. In VR, it is first rotated and then stretched. So, because R is an orthogonal matrix, orthogonal tensor, a multiplication with itself gives the identity matrix and first isolate U or V. So, strain is the measure of relative distance change between two material points after a deformation. So the distance between two material neighbor points in the material configuration is the differential dx, upper dx, and the spatial configuration lower dx. So like already addressed, the right and left stretch tensor U and V are the candidates for building a strain quantity. They measure pure material deformations. And to access them, we have to start with an expression where the orthogonal tensor R cancels itself out. So the simplest start is how the square of dx deforms. By taking the square, we ensure that the deformation gradient tensor is multiplied with itself. So we set dx to the power of 2 equal dx times dx equal f dx, material dx times f dx. And by identification, we find, as expected, the corresponding square mapping and a factor of interest, the right Cauchy-Green tensor C. It is the square of the right stretch tensor U. So C, the right Cauchy-Green strain, is transpose of F times F equal U to the power of 2. So further, we get the left Cauchy-Green strain tensor, which is B equal F times transpose of F. It's also equal square of V. We also have the Piola strain, small c equal a transpose of inverse of F times transpose inverse of F. It's also equal the inverse of a left Cauchy-Green strain. Till now, all these strains are basic strain tensors, describing slowly stretches. The Lagrangian strain tensor E compare these stretches to the undeformed shape, making it more sophisticated and becoming the aforementioned definition of strain as the relative shape difference. It is the most used strain definition, at least in engineering field. So if we set F and C, which we've already seen, E is equal 1/2 open bracket transpose of F times F minus identity close bracket. It is also equal 1/2 open bracket right Cauchy-Green tensor minus identity close bracket. We have a final expression of E also, which is 1/2 open bracket gradient of U, also the displacement U, plus transpose of gradient plus transpose of gradient times transpose of gradient, close bracket. And in case we deal with infinitesimal strains rather than finite one, like we see till yet, E can further be simplified by cancelling the last term, the product of the derivatives tending to 0. We end up with E equal 1/2 open bracket gradient of U plus transpose of gradient of U close bracket. It's also equal epsilon. Infinitesimal strain, also small strains, are widely used in mechanical and civil engineering. So from the general definition of a Lagrangian strain tensor E, a whole family of strains have been derived by Set and Hill, all admissible as long as the second order symmetric positive definite nature is preserved, as long as they are also compatible strains, meaning they are continuous, monotonic, overall derivable with respect to the displacement gradient, and the deformation field can be get back from them. It's very important. That's the definition of compatible strains. These admissible strains must also be reduced to the same infinitesimal strain when needed. So the Set-Hill strain family reads En equal 1/2n open bracket C to the power of n minus identity close bracket. So n is a real parameter setting the specific strain tensor. So as example, we get the Almanzi strain, which is the case where n is -1, the E -1 equal 1/2 open bracket 1 over the right Cauchy Green tensor C minus identity close bracket. We have the Henke strain, also called the true strain, the natural strain, when n is null or 0, A0 equal 1/2 ln of C. It has this true and natural character because in the course of the displacement and deformation, the updated shape is used in the strain calculation rather than the fixed starting one, like other strains measure use. But this comes with the cost of continuously determining the updated shape. We also have a Bayard strain when n is 1/2, giving E 0.5 equal C to the power of 0.5 minus identity. And lastly, but not exclusively, the Eulerian strain, the counterpart of the Lagrangian strain in the special configuration, a small e equal 1/2 open bracket identity minus transpose of the inverse of f, the deformation tensor, times inverse of f, close bracket. It's also equal 1/2 open bracket identity minus small c, close bracket. Remember, the capital letters stand for material configuration and small one for spatial configuration. So we can switch to the counterpart of a quantity in another configuration by doing a pullback from spatial to material configuration and a push forward in the reverse direction. For example, pulling back the Eulerian strain from the spatial to the material configuration in order to obtain the Lagrangian strain is E equal transpose of f times small e times f. If we want to go from the Lagrangian strain to the Eulerian one, we can do Eulerian strain equal transpose of inverse of f times Lagrangian strain times inverse of f. So basically pull back and push forward to switch configurations. So in a Cartesian XYZ reference frame, the strain tensor have values in three principal directions, where they are only mean to max stretching or compression and no sharing. The strain tensor are symmetric, therefore there exist three orthogonal directions, meaning independent to each other, and three eigenvalues, which are the magnitude of these strains. The eigenvalues are the stretches, the eigenvectors, the directions, which eventually has to be normalized. So the starting equations in determining the eigenvalues and eigenvectors is the characteristic equation, determinant of open bracket E as Lagrangian strain minus lambda times identity close bracket. It is equal lambda to the power of 3 minus 1e times lambda to the power of 2 plus 2e times lambda minus 3e equals 0. So the in EE, 1e, 2e, and 3e are invariant of the tensor. Like the names indicate, invariants of a tensor remain preserved even if the reference frame is changed. So the roots of the characteristic equations are the eigenvalues. So the result is the far more simplest tensor that we see in the right side. The diagonal elements are the eigenvalues lambda 1, lambda 2, and lambda 3, and the off one are all zeros. With this result, we can rewrite the strain tensor in an alternative form called spectral form. It reads E equal sum from I equal 1 to 3 over lambda I times dyadic product of EMI, EMI. So equal lambda 1 times EM1 plus lambda 2 EM2 plus lambda 3 EM3. So EM1, EM2, EM3 are the Cartesian reference axis unit vectors. M stands for material coordinate. Also, the invariants can simply be rewritten as 1E equal lambda 1 plus lambda 2 plus lambda 3. 2E equal lambda 1 square of lambda 1 plus square of lambda 2 plus square of lambda 3. And 3E is lambda 1 times lambda 2 times lambda 3. Bear in mind that this rule is applicable to all symmetric quantity tensors. So first, we can rewrite in spectral form a lot of quantities we've seen until now. And we can, for instance, easily calculate products, exponents of or roots of tensors and their derivatives. So the strength tensor can be decomposed in an addition of two terms called spherical and deviatoric parts. Like the name suggests, the spherical part is responsible for the volume change through hydrostatic pressure, and the deviatoric one for shape changes through shear deformation. There is sometimes an interest to identify these parts, for instance in plasticity, where plastic flow is caused by the deviatoric part. So taking the Lagrangian strength tensor, we could have taken every strength we've seen until now. We get E equal spherical part plus deviatoric part. The ES, the spherical part, is 1/3 times trace of E times identity, and the deviatoric part is simply E minus the spherical part. Now to the material time derivative. Quantities can change with time, and to express this, we need to do material time derivative. So in case we deal with material coordinates, which is upper X, the operation the first equation is straightforward. Derivative of t with respect to time is partial derivative of t simply. Also t being a quantity in the material reference. But in case we have spatial description of a quantity where the spatial coordinates also depend on time, we have to apply the chain rule, which leads us to the second equation. Material time derivative of t is equal partial derivative of t with respect to time plus velocity in spatial configuration times gradient of t. Gradient of t is of course with respect to the spatial coordinates. So an application of a time derivative of strengths is, for instance, the case where the material shows viscosity behavior. In this case, the strain rate is crucial in capturing this behavior in constitutive equation. So we present some strain rates, which derivation can be found in every relevant textbook about continuous mechanics. First, let us set the gradient of velocity as L of xt. This gradient velocity has a symmetric part called d, describing the rate of pure deformation, and an antisymmetric or skew part called w, constituting the rigid spin or rotation. Velocity gradient L of Lxt equal gradient of velocity. It is d plus w. So the rate of deformation d is equal 1/2 open bracket gradient of velocity plus transpose of gradient of velocity, close bracket. And the spin is W equal 1/2 open bracket gradient of velocity minus transpose of gradient of velocity, close bracket. So with L, D, and W, we have a deformation tensor rate, which reads F dot equal LF. We have a right Cauchy Green tensor rate. C dot equal 2 transpose of F times D times F. The Lagrangian strength rate. E dot equal F transpose times D times F is also equal 1/2 of C dot, the right Cauchy Green tensor rate, 1/2 of the right Cauchy Green tensor rate. And lastly, we have the infinitesimal strength rate, which is epsilon dot equal simply D. In the infinitesimal case, the strength rate is simply the symmetric part of the velocity gradient. It is also one of the few objective strength rates, meaning it is independent of reference changes. Some are not suitable for reproducing properly a rate-dependent material behavior without some accommodation. So a core imperative rule in continuum mechanics for quantities is objectivity. It refers to integrity preservation of a quantity regardless of a reference frame from where it is read. So the reference frame can be displaced by rotation and translation, but this must not affect the value of a quantity. So to ensure that tensors must comply with a test. If it fails, it's not objective. For a first order tensor like a vector, so Z in the new reference frame is equal Q times Z in the old reference frame. Q is the rotation tensor. So for a second order tensor, we have Z prime equal Q times Z times transpose of Q. For example, the displacement is an objective first order tensor because if you set 2 points in an old frame which are XA and XB, in the new frame we have XA prime equal Q times XA plus C, and XB prime equal Q times XB plus C. C is a constant, a translation constant, and if we define U as XB minus XE, we get U prime equal Q times U, which passes the objectivity test. The velocity is not objective because we have V prime equal Q times V plus Q dot times X plus C dot. The last two terms, Q dot times X plus C dot, make the test fail. Fortunately, there are ways to surpass such failure by rewriting the derivative, such as the spin tensor W comes to use and cancels out the terms which fail the test. One of the alternative derivatives is the Zarembra-Yeoman rates. Both rates pass the test. You can check it. Of course, feel free to check the objectivity of second order tensor we see so far. So now we come to the end of the presentation. To summarize, a body motion in the context of the continuum mechanics is the displacement of a continuum body from one configuration to another. In this case, from a material configuration to a spatial one. So, a Lagrangian description of a body quantity is expressed in material coordinates. Eulerian description in spatial coordinate. So Eulerian description is in spatial coordinate and spatial configuration, and the Lagrangian description is material configuration. So the second order deformation tensor F measures the deformation of a line, but it also registers rigid body motions. It can be decomposed in those parts. We've seen that F is equal R times U, for example. R being for rigid body motion and U for the actual deformation, the stretches. There are different types of strain tensors. The right Cauchy-Green strain C, the left Cauchy-Green strain B. We have C, a strain in spatial coordinate or spatial configuration. We have the Lagrangian strain E. We have the infinitesimal strain epsilon, etc., etc. We also have a whole family of strain, the set-Hill family, derived based on the Lagrangian strain. Symmetric tensor-like strains can be simply rewritten in spectral form, where diagonal elements become the eigenvalues of the tensor and the off-diagonal zeros. This form eases further use of the tensor, like multiplication and so on. Strain tensor have a spherical part responsible for volume change and deviatoric one for shear deformations. And of course, we can decompose this strain tensor in both parts. Objectivity or reference frame indifference is not kept by all continuum quantities like some strain rates. And we've seen that objectivity is very important in continuous mechanics and so on. It's very important that the quantities are objective. It means whenever the reference frame change, these values, the values of these quantities should not be changed, should be preserved. So we've also seen that there are alternative rates like the Zarembra-Yeoman rate, which reinstate objectivity for strain rates which are not objective, for example. With this, we are at the end. Thank you for being here. Let me know your remarks in the comments. If you like these kinds of contents, click on the notification bell or subscribe for new videos. Goodbye and see you soon.